Thank you. Okay. Yeah. Let me try to share my screen.
Sorry, I should have waited for it.
Yeah. Sure. Okay. So thanks everybody for staying until my last lecture. I'm going to continue my discussion, our discussion of the fermionic particle vortex duality that we started last time. Trying to think about last time we were motivating this particle, this fermionic particle vortex duality as some way to explain the phenomenology of the fractional quantum Hall state. But today I'm going to try to derive this duality using something that we would call a seed duality, something that presumably more fundamental, and you will see that it has some reason. We might hope that it is actually correct. So what I'm going to say today can be found in this review that I have written a few years back. So let me first recall what was the content of the fermionic particle vortex duality. Okay, so the statement is that if we have a theory, so let me write on the two sides of the slide, two theories that are supposed to be equivalent to each other. So the first theory is the theory where the action is the sum of the three-dimensional field. Say we were for definiteness, let me write down also for the F mu neutron that it coupled to. So here we have some kind of a brain word on which there is a chiral fermion, two-component fermion, say capture on a domain wall, and then it's coupled. This two of these fermion would be interacting by a Coulomb force, but the photon, the electric field line can be in 3+1 dimension. Okay, so that theory is supposed to be according to the statement of the duality. So let me call that E. Psi E is the electron. Psi bar gamma mu d mu minus I A mu psi plus minus 1/4. So this is three-dimensional, 1/4 pi ADA. And then again, there is this 1/4 E squared D x at mu square. So that would be a remarkable statement if we can make it work, that these two theories are dual to each other. If this statement is correct, it would be a remarkable duality. So on the left side, for example, if you think about the interaction, imagine that you can think about integrating out a mu. So since it's quadratic field, you integrate out, you get a current, non-local, some kind non-local current interaction. I'm not going to write it. There's some kernel here, x minus y mu. But we know that the strength of the interaction here would be governed by E square. Right? So E square is the coupling constant on the left-hand side. And on the right-hand side, if you do exactly the same thing, that is integrate out Now we have to integrate out both A and A. You find exactly the same non-local interaction with the same kernel, but except that the coupling constant here would be 1 over E squared. So the duality that we have here is truly strong weak duality. Map a weakly coupled theory on one side to the strongly coupled theory on the other side. Right.
So can I ask a question?
Yeah.
How is this a particle? Maybe you said that yesterday, but how is this a particle vortex duality? Because both sides are gauged, so like they're on the lattice, there should be no particles, maybe because both sides are gauged.
Both sides are gauged, but let's take a limit. Say let's take a limit E squared goes to 0 on this side. On this side we have a theory, basically a free Dirac fermion.
Right.
Free Dirac fermion. On this side we just have a psi Lagrangian, which is Lagrangian of psi coupled to a field, and then minus 1 over 4 pi LDA. Right, so this is a background, just a background field. Just tell us that how we define current. All the dynamics of the theory is here.
You would add a dynamical field for A as well, little a.
Yeah, coupled to the psi. And so the duality here at the first site, well, at the naive level, is the duality between a free Dirac fermion and a Dirac fermion coupled to a gauge field. We know that if we have a gauge field in 3 dimensions, its coupling constant runs to infinity in the infrared. The theory of fermion. So let's recall some fact. If we have some fermion, let me take n fermions. So we have n fermions coupled to a U1 gauge field. Right. Psi, common U, sum over A from 1 to n, Lagrangian. A d mu minus IA mu, and because I minus 1 over 4 E squared of mu square. In the limit when n is large, we know, so if it's defined that in 2 plus 1D, in the limit when n is large, we know that the theory is conformal. It's a conformal field theory. Why n is large? Large n makes the theory more understandable. That we can think about the modification, radiative correction to the propagator of the A field. The fermion loop introduce a factor of n into the polarization tensor, and so the propagator of the photon propagator is 1 divided by d0 minus 1 plus n times that graph, and that is of order 1 over n when everything is computed. And so the interaction between current mediated by a photon line is suppressed by 1 over n. If I have 2 currents interacting with each other, I have to insert a lot of this fermion loop, and that introduce a 1 over n. So effectively, the theory is weakly coupled in the large n limit, and we can understand everything about this theory. In particular, one can compute all critical exponent with the fixed point. Now, it's not clear what happened when n is small. So before this fermionic particle vortex duality was suggested, people tried to determine what is there a minimal value of n where the theory remains conformal using not very rigorous calculation. And it seems that the theory would be gapped at sufficiently small n. N is less than some critical n, and I forget what critical n was estimated in the literature, but it was believed that 1 is less than that NC. And so the question is, I think this question is still open, whether this duality is actually correct or it's only serves as a guide to understand the fractional quantum Hall problem. In order to understand the fractional quantum Hall problem, we need to make use of this duality at finite, infinite. So the fractional quantum Hall problem requires introduction of non-zero magnetic field on this side, which, as we said, is correspond to a non-zero density on the other side. Which is while on the other hand, the duality, if it is the strongest statement of the duality, will be valid for zero magnetic field on the left side and zero density on the other side. And that is something that is not completely at this moment. I'm agnostic myself about whether that statement is correct. Now, another thing that makes it make this statement a bit strange is something called parity anomaly. And this is something one has to, I hope to clarify the problem, the issue later in the talk. So here we know that if we have one two component spinor psi coupled to a mu, then if we regularize the theory is not invariant under parity transformation. Basically, if we compute the one loop graph where the fermions run in the loop, right? And we have to regularize the problem by introducing say a Pauli-Villars field, and that Pauli-Villars field would breaks the parity symmetry of the theory. So when we write this theory, we pretend that it's parity invariant. It has parity. So what does it mean, this theory? What does it mean? This theory, before taking e go to infinity, how we define the coupling of a single two-component fermion to a gauge field A mu. Okay, so but let's forget about this problem and try to see what it implies for the fractional quantum Hall effect again. So here in the fractional quantum Hall effect, we encounter another very strange feature that I want to highlight here, which I don't understand. I think it's good to talk about things that we don't understand. Uh, so let's take the limit again in the on this side. E square goes to 0 at non-zero magnetic field, and we said previously in our discussion that there was a strange things that prevent us from understanding the ground state. That is, if the limit E goes to 0, we are supposed to pick the ground state by filling up some of this state with E equal to 0. We know that all the Dirac sea has to be filled. All these states are empty, but there is a ground state degeneracy. With the basically we have 2 to the power of 1, the number of magnetic flux quanta going through the system. But that means that this, if we map to this theory, this is a theory where we have fermion coupled to the A field, to a gauge field, and the statement would be in the zero non-zero density. The system has exponential degeneracy. And we cannot rule that out. We cannot prove it. This is a strongly coupled theory, but it is very unusual things that happen in quantum field theory. That if we take the system to finite density, suddenly the ground state is exponentially degenerate. And the exponential degeneracy is lifted only when we put in additional interaction. For example, when we reintroduce this 4-dimensional gauge field capital A mu. So this is another thing that that is not understood at the moment. Any questions for me? But if not, I'm going to tell you what probably I think is the best way to best approach, best hope for us to understand the particle vortex duality in the case of fermion. And this involves an idea called flux attachment. But in the context of duality between different quantum field theories, it becomes quite non-trivial. So the idea of flux attachment is the following. Maybe I first write down the statement in words. So the statement is that if we have a boson, phi coupled to a Chern-Simons, so it's all in 2+1 dimension. Field A mu, say with level 1 kinetic charm for action for A, ADA, 1/4 pi ADA. That theory is the same as fermion. The particle statistic changes from being a fermion to being a boson. So what is how one can understand this at the intuitive level? So I have a particle, say a boson. It's coupled to, yes, imagine we have a particle. So we know that a particle coupled to my gauge field like G mu A mu. And when I have a Chern-Simons gauge field unit coupled to the Chern-Simons gauge field, it's possible to solve the equations for A. You have 1/2 pi dA equal to J. That means if I have a particle at rest, it creates a magnetic field. Like a solenoid now. This equation tells me that the magnetic field is concentrated at the center. But so what I draw here is how AI would looks like at different point in space. Curl of A is equal to B. That is 1/2 pi B. B now is a delta function at the location where the particle is. So it's like x minus x0. Now a particle is surrounded by like a pure gauge, a mu field. So that means that if I take two particles and exchange the adiabatic exchange of their position leads to Aharonov-Bohm phase. Why? Because exchanging two particles is equivalent to taking one particle in a half circle around the other one, and then translate the whole system by the distance between the two particles. And one can check that this, the Aharonov-Bohm phase is equal to -1 if the Chern-Simons term in the action is level 1. This idea has been known for a long time, that in two-dimensional fields coupled to a Chern-Simons field would transmute its statistics. But only recently has this been formulated as a statement about the duality between two conformal field theory. So let me write down this statement. The statement is that if I take a Lagrangian, which is a Lagrangian of a complex scalar field, phi. So my phi would be scalar field and psi spinor field, fermionic field. If I have this coupled to ADA, and here I have to write down also minus lambda phi to the 4th, right? And then minus m square phi square. Right? This is dual. This is the same as a theory of fermions. With its own mass term. And the statement is at the critical point, near the critical point, these two theories are equivalent. A scalar coupled to a gauge field is equivalent to a free fermion. We understand the theory of free fermions very well, but on the other hand, we don't understand the theory of a scalar coupled to a Chern-Simons gauge field. If the number of scalar is very large, the theory on the left is clearly a conformal theory. You can just compute, find its critical point. But the assumption the assumption here is that this critical point survives even when there is just a single gauge field. And that is unclear at this moment whether that statement is true, that there is such a critical point. But let's accept that as working hypothesis, and then try to extract consequences from that statement.
Yeah, I'm just wondering, why do we need a large number of gauge fields in order to be a conformal field theory? I thought like in near critical points it was like automatically conformal.
Oh, if I have one U1 field little a, but a large number of scalar, then one can show that this theory will have a critical point. The ON or O2N scalar coupled to a single U1 gauge field will reach a critical point, will have a critical point. Basically, it's some Wilson-Fisher critical point distorted by coupling to a gauge field. But here
we cannot show like whether the critical point exists when we only have like a few species of gauge fields. That's correct.
We cannot, and here we actually have some surprises. Why we need to be very careful with the with saying what we know. So, for example, let me give you one example. We know, remember this bosonic particle vortex duality. This bosonic particle vortex duality map a scalar, Wilson-Fisher field theory, basically scalar field theory, to a scalar coupled with a gauge field. Now, here, for a long time, there was a question whether that theory exists. And people try to do epsilon expansion. And what they conclude is that in epsilon expansion, the theory is conformal only when the number of the scalar, complex scalar, is larger or equal 183. So when n is equal to 1, the belief was that the theory would not have a fixed point. And it turned out to be untrue. The epsilon expansion is completely not reliable. So it could be that the situation here is also similar, that this theory actually exists as a quantum field theory, though we don't have a analytic way to show it, and numerically it's also difficult because of the presence of Chern-Simon term in the action. It's harder to simulate. Okay, so let's assume that this is true. To go further, it's nice to have some shortened notation. So I'm going to write this Lagrangian is simply a Lagrangian.
Can I ask a question?
Yeah, sure.
Yeah, could you match the symmetries on the two sides? I see these two U1 symmetries on the fermion side. I'm not sure what they map to on the bosonic side.
So there is a U1 symmetry on the fermionic side. The U1 particle number, I can add here explicitly a coupling of a mu to that particle number. So this is a conserved charge, and the equivalent conserved charge here would be 2 pi a dA, Chern-Simon's term. So the number of fermions on in the fermionic side is the flux quantum of little a field on the other side.
And the axial symmetry? Oh, you're in 3 dimensions. Sorry. Yeah.
I'm in
no.
three. Yeah, I'm
Yeah.
three dimensions. So
I
there is no
remember.
axial symmetry.
All right. Thank you.
Yeah, that reminds me of another check that one can make. So let me do this check. But before that, I'm going to shorten the notation. So I'm going to write this as L equal L of phi A. That is just phi with all the phi force and mass coupled minimally to A plus 1/2 pi A dA is dual to a theory which is a fermion coupled minimally to A mu. A is our external field. Okay, so let me call that equation 1. It's a statement of let's call that a seat duality. And from this seat, we are going to obtain some further consequences. Now, one check of this seat duality is to imagine that we are in the gap phase. We take for example the mass of the boson, mass square of the boson, to be larger than 0, or let's take it going to infinity, plus infinity. And I'm sorry, here I forgot something very crucial. This would not be correct in the way that I wrote. Plus 1/4 ADA. It's a scalar coupled to Chern-Simons field, not scalar coupled to just a Maxwell gauge field, but it has to have a Chern-Simons term in the action. If now phi is massive, then basically I can just integrate out this term. Phi decouple, this term completely goes away, and I have in the theory just, let me say that, L is 1/4 pi ADA plus 1/2 pi ADA. All right. And then I can take this, I can integrate out over dA. It's just quadratic integration. The saddle point is when the equation for the saddle points dA plus dA equal 0, which means A is minus capital A, and the action becomes minus 1/4 pi ADA, I think. Okay, so what is the free fermions here? But here is something that we have mentioned before. In order to couple a fermion, so we have this fermion coupled to the A mu field, right? This theory would not be well defined if we don't specify what we do with the Pauli-Villars regulator. Roughly speaking, we have we compute when we have in the free fermions, when the mass of the scalar goes to infinity, basically it corresponds to the mass of this fermion also going to infinity. So we compute this diagram, right? And what we find is that this diagram is giving us 1/8 pi times AdA with some coefficient dependent on the sign of the mass of the fermionic field. It's either plus 1/8 pi AdA or minus 1/8 pi AdA, depending on the mass of this fermion. The Pauli-Villars regulator would be a field which we choose to have a large mass, and we have to add that to the calculation of the polarization tensor, and that one will add, say, depending on the choice of the sign of the Pauli-Villars regulator, can add, for example, 1/8 pi AdA. So let me choose the sign of the Pauli-Villars regulator to give us minus 1/8 pi, because in that way I can say that if my mass of the fermion is such that, say, the fermionic, so here let me choose this mass of the fermion to be less than 0 and goes to minus infinity, then I get minus 1/8 pi AdA minus another 1/8 pi AdA from the regulator, and give me 1/4 pi AdA, which matches with the calculation in the bosonic side. But that means that if I take the mass of the fermion to go to infinity, to go to plus infinity to the other side, I should have plus here minus and goes to 0 times AdA. So let's see how that maps in the bosonic case. In the bosonic case, then it's the opposite limit when the phi goes to minus infinity. The scalar field has negative mass square, and we are in the Higgs phase. So we are in the Higgs phase. That means that this term basically suppresses all the fluctuation of the capital A field, so of the little a. So if we are in the Higgs phase, this little a basically becomes massive, and they cannot fluctuate. If they don't fluctuate, then all these terms have completely disappear. So that means here we have nothing. We have 0. Basically, that's what we get after integrating out the little a field. Particularly, there is no AdA terms. And that means that we also have matching between the fermionic of the duality and the bosonic side of the duality. Right? The two phases of the bosonic theory, the Higgs and the Coulomb phases, correspond to two different sign of the mass of the fermions. Any question? So in fact, what we have said here is that in order to define the fermionic side of the duality, I'm going to take the fermionic theory and add to that the contribution that we would get from the Pauli-Villars regulator. So this is the theory. More precisely, this is the theory that is dual to the bosonic theory coupled to a gauge field.
That's a question.
Yes, sure.
If you consider the bosonic theory with a scalar particle that has charge greater than 1, so that you can now Higgs down the symmetry to some finite group instead of Higgsing it down to 0. Can you compare the finite group theories that are left over in the n squared goes to minus infinity limit?
You mean if I gauge?
So here you're gauging the entire group away. So I'm asking if it is possible to gauge the group away in such a way that some finite group is left over.
I'm not completely sure. Yeah, what would be the fermionic dual of that theory? Because the statement here, the statement that we have here is specific for the for theory coupled to for charge 1 boson.
Yeah.
If you have charge 2 boson coupled to a mu, the technique that I'm going to describe might actually be, I'm not sure if it will, it might be that the technique that I'm going to describe now would give us some answer to that question, but it is an exercise that I haven't done.
Okay, thank you.
Yeah. So to give you the flavor of that kind of exercise that one do, I'm going to derive from this duality another duality. So the duality that we have, let me write again, is the duality between phi coupled to A, small a, dynamical gauge field plus 1 over 4 pi AdA plus 1 over 2 pi capital AdA. Capital A is always background. Small a is dynamical, is fermion, and here I'm careful including the term obtained from integrating out the Pauli-Villars regulator. Okay, so these two theories are dual to each other. So the trick that the exercise that I'm going to describe are done in paper by Karsh and Thong, and another paper by Senthil, Seiberg, Wang, and Witten. And it consists of the following. Let's gauge the A, capital A, promote it to a new gauge field. Basically here we replace this A. We say that this A is now replaced by a new field. Let me call that BDA. Okay. So basically in path integral, you imagine that this A is no longer parameter in the path integral, but we integrate over this A. So now we have a new duality between the theory on the left, which has 2 gauge field, L of phi A plus 1 over 4 pi AdA, plus that is dual to a theory in which this A is now promoted to a gauge field. And in the path integral, we integrate over. So the statement, the expectation here is that the bosonic partition function before this A was promoted to a gauge field was the same on the two sides, so we just integrate over A, and then make a statement about the duality between two field theory. Of course, we can also add to the theory a background field. Now A field coupled to dB. Since we add the same thing on the two sides, the duality is not destroyed. So this is the way we get the new duality. But this now this duality can be simplified. On the left hand side, simplified by integrating out B. When we integrate out B, we get the constraints. Since B appear in linear order in the action, we have just dA plus dA equal to 0, or A equal minus A. So after integrating out B, the left-hand side will be phi minus A, basically plus 1 over 4 pi ADA. You can check that is the case. So the left-hand side actually is simpler theory now. It doesn't have a gauge field. The gauge field is integrated over. First, we're integrating out B to get constraint that A is equal minus A is basically a delta function. And then we integrate our A, right? Set it to be equal to minus A, capital A. And so we get a new duality. Basically, it says that boson, a free boson, is equal to a fermion coupled to a Chern-Simons field. It's a reverse of the previous situation when the boson coupled to Chern-Simons is a free fermion. Here we have a boson. Here we have fermion coupled to Chern-Simons field is now a boson, but it is not a free boson, but it is a Wilson-Fisher fixed point of the bosonic theory. So we get a new duality that way. Note that here I have minus A, but due to charge conjugation symmetry of the two terms, I can flip sign to plus A without any problem. Can replace by plus A here using charge conjugation. That's the form that I'm going to use. L phi A plus 1 over 4 pi ADA map to just a fermion coupled to a Chern-Simons gauge field plus 1 over 2 pi ADB.
I have a naive question. This Pauli-Villard's regularization term also looks like a Chern-Simons term, right? So,
yeah, that Pauli-Villard here.
Yes.
This Pauli-Villard here is just a Chern-Simons, but in terms of the I would say the external field. It's not a dynamical Chern-Simons term.
But I mean, why would you say that the left-hand side is a free boson, whereas the right-hand side has a Chern-Simons? Because ADA term looks like a capital ADA on the left-hand side, also looks like a Chern-Simons. So there is a Chern-Simons field also on the left-hand side, right? Or
there is a Chern-Simons on the left-hand side, but this Chern-Simons is a dynamical field. We are supposed to integrate over little a. While on the right-hand side, what we have is just field psi in the background A, background capital A.
But there is a connected term for A, but we are not integrating. There is a connected.
Yeah, before going to this step, I didn't integrate over A. A was just some parameter. So this line, in this line, my capital A is not integrated over.
I see.
Just background. In that case, psi is just some free fermion.
Okay. Yes.
But but in order to define what I mean by current correlator in the theory of psi, make it consistent, I have to add this term. Otherwise, there is this so-called parity anomaly. So the theory is not invariant under certain background under certain large gauge transformation. Okay, so it turned out that now this from this duality. So now we have our knowledge of duality is now multiplied. We have this duality on the top line from which we derive the last line of duality. So there are two kind of duality. And we also can double the number of duality that we know by doing time reversal. We get two more equations, time reversal flip sign of the Chern-Simons terms, like ADA, ADA, ADA. I'm not going to write them down, but we have four. In this way, you get four different duality. Any question? Okay, so now I'm going to show you one miracle. Actually, there are two miracles, but I'm going to show you only one. That is how to derive. I can derive the particle vortex duality from this seat duality. So these four of these seat dualities that come out from just one, but I can derive the particle vortex duality. So this seat duality is duality between boson and fermions, while the particle vortex duality is the duality between boson and boson, or fermion and fermion. So that particle vortex duality is derived by applying, it's basically a seat duality square. We leave the seat duality, we iterate it twice in certain combination, and then we will get this particle vortex duality. So how do I do that? It's actually it's actually quite straightforward, although it's, there are many steps we have to do. And so I'm just show you the schematically how it's done. So we know we start from a seat duality, in this case, free boson, or not free, Wilson-Fisher bosons is dual to fermion coupled to a gauge field. The one that I wrote on the last line in the previous blackboard, 2 pi ADA, except I pull the capital A to the right hand side. This capital A is not a dynamical field, and so we can just move it back and forth between the two sides of the duality. This is just some contact term, not a dynamical field. Okay, so I'll just show you the steps, and each of these is very trivial to do. First, we promote capital A to a gauge field, to dynamical field. So again, I have phi. Now capital A on this side, I can call that small a plus, and I add to that term ADA. Capital A is now a new field. This is new. The old A is promoted to a small a and integrated over. The left hand side, I can do that. I replace all this A by a new B, BdB, and then add here 1/2 pi AdB. And then on the right-hand side, I integrate over B. Okay, so that is an exercise, trivial exercise that we can do, just 7-point approximation. We get at the end of the calculation, we get something like this. So I'm just writing down the answer: 1/2, 1/2, 1/4 pi ADA plus 1/2 pi ADA plus 1/4 pi capital ADA. But this is, if we applied one of the 4 seed duality, that map onto a theory of some scalar field coupled to an A field. So one of these 4 seed duality involve mapping the theory that is obtained by integrating over B to the theory of a simple scalar field coupled to A. So this way we derive the duality between a boson, a Wilson-Fisher boson, to a Wilson-Fisher boson coupled to a gauge field. Or this theory is also called the abelian-6 model. And now one can also modify this procedure to have
the abelian Higgs model. You did not have a Chern-Simons term for little a. You had a F mu nu squared term for little a, but here you have a.
This is not the this is
little a for a small field. A. For a small a.
Yeah, there is no Chern-Simons term here either for small a. Here, if I couple, I make A to be a dynamical field, but I didn't add any Chern-Simons to the action. I just integrate this over A without adding any Chern-Simons, and so that's okay. Yeah. Okay. This is what I get is the A. What you suggested is actually what is also useful. If I take this theory on this side with phi A and then promote that to small a, but then add the Chern-Simons ADA. Add the Chern-Simons. And then add another like 1/2 pi ADA. And then do the same thing for the dual fermionic theory, Also promote A, add Chern-Simons. Then what one can show is that we find this fermionic particle vortex duality. Because the left-hand side, you can see the left-hand side, we add the Chern-Simons term before integrating over small a. And that theory is boson coupled to a flux, that is a fermion. Free fermions. So on one side we have free fermion, and on the other side, turn out that we will have fermion coupled to a gauge field. Okay, so detail you can find in the reference that I put on my first slide. my review in 2018. Okay, so let me just give you the detail of this theory, a little bit detail of the result. So now that this procedure gives us a theory that is slightly different from the theory that we call fermion coupled to a gauge field. After this procedure is done, at one step, we get a theory of a fermion coupled to A minus 1/2, 1/4 pi AdA plus 1/2 pi AdB minus 2/4 pi BdB plus 1/2 pi AdB. Okay, so then here is the subtle step, integrating over B. So the equation of motion that we get for B is 2 minus 2 dB plus dA plus A equal to 0. So naively, if we take B equal 1/2 of A plus A and put that into these equations, we find the result, which is our Lagrangian that we have. Lagrangian would be equal, the final Lagrangian would be equal to some phi coupled to A plus 1/4 pi AdA plus 1/2 of 1/4 pi AdA. Okay, but it is only a naive, this naive procedure neglects certain subtlety with the quantization of the flux of the gauge field. So if we have a U1 gauge field in a compact manifold, its flux is quantized to 1. So if the total flux of capital A and small a here sum to something that is odd, then this B, the second point doesn't exist. It's a configuration with flux of B that is odd, that is half integer, and the complex manifold is not legitimate. And so only if we do this naive integration procedure, we get a theory that we have written in the beginning as the candidate for the dual of the free fermions. So on this side, the free fermion is obtained without any of this subtlety. On the other side of the duality, when we do this procedure, we get the theory of a fermion coupled to a gauge field, but the Chern-Simons, this mixed Chern-Simons term has half of the quantized values, and this is the consequence of the fact that when we integrate over one of the gauge field, we have been a bit cavalier with the global issues. So strictly speaking, the theory that is dual to free fermion is this theory, but written in this way, certain we don't see all the discrete symmetries as clearly as if we write the theory in a more naive form. Okay, so is there any question so far?
I guess I have a question, Professor.
Yeah.
I guess do you have an idea of how to extend this this construction of the heat kernel off of the lattice?
Which which construction you have in mind?
Just I guess what I'm asking is, do you have a physical interpretation for these last four terms?
This term? Or which term?
Yeah, exactly. Those four. Is
Yeah.
there a physical analogy? Just I guess from first principles.
On the lattice. So I can let me point you. Maybe I'll give you a reference. So this duality between fermion and bosons is a C duality. There is an attempt to derive it. So to derive a lattice derivation is basically a map between a theory that we think is discretization of one side of the duality and the discretization of the other side. So this is by Chen. 1705 05 841. So how do they deal with how do they discretize the Chern-Simons on the lattice? Chern-Simons term is very difficult to put directly on the lattice. So what they have to do is to put to realize the Chern-Simons like ADA as a couple to a lattice fermions psi, and this lattice fermion has some topological band. That is a band, a field band, which when we integrate over this field band, we get effective ADA term in the action for the gauge field coupled to it. And so by discretizing the Chern-Simons term, that way they can show that there is a way to understand the emergence of the duality between a boson and a fermion on the lattice.
Okay, yeah, that's sorry, thank you.
Yeah.
Soon you have about 5 minutes.
Yeah, I think I've done, but I can point out some things that I'm going to just mention some results that I think are notable. One result that is notable is by Senkeshu. Can also be derived from this duality can be derived from the C duality, but I think but it can be derived from just from the fermionic particle vortex duality. So it can be derived from the less elementary duality. So this is a statement of the self-duality of the theory of two fermions coupled to a U1. So if I have Lagrangian like this, where A run from 1 to 2. Okay, so this theory is already easier to put on the lattice since they have two fermions. Right? Don't have to violate the fermion doubling. So the claim is that this theory is self-dual in the sense that there is a map, the map of this theory to itself, a theory that looks like itself with a different gauge field. And the map is between, say, for example, this operator on this side is mapped to epsilon mu lambda d mu a mu on the other side, and vice versa. And so in the fermionic duality, this fermionic duality is the duality between a fermion and a fermion coupled to a gauge field. Basically, when we apply this duality to the left-hand side, we get we can apply the duality, integrate out some of the fermion, and convince yourself that the theory that one obtained has the same form as the original theory. But the identification of the currents is now completely non-trivial. So in particular, this is something that at least a few years back, I haven't checked the recent literature. There is some lattice evidence that this theory is a conformal field theory. There is a conformal fixed point correspond to two fermions coupled to a U1 gauge field.
Sorry, is the duality then the same? Is it the same as saying that these two operators are the same operator? Like, because you're mapping the theory to itself, and then you say that
these two operators are distinct, but they must have the same critical exponent. Okay,
but then why are they different? Like, what is different about these two operators? Like, just from a like CFT
there are two
point of view?
operators. So there are each of the CFT has two operators. But the duality map this operator from one side to the operator on the other side. So this psi operator on the dual side is not the same as the psi operator on the left side. So psi tilde is different from psi. So that psi tilde gamma mu psi 1 minus psi 2 tilde gamma mu psi 2 is equal to this one, and this one is equal to that one. Right?
From a CFT, abstract CFT point of view, they are the same operator. Like, they have the same dimension, and maybe the OPE coefficients are also the same. So, how are these two different operators? Just from let's say somebody were to bootstrap, then is there one operator or are there two operators? Because they have the same dimension.
Yeah, these are as I understand that I'm not completely sure, since I haven't studied this to be honest carefully. there is something strange here. That is, this theory has a SU2 global symmetry, right? This is a SU2 global symmetry. And this one has a SU2 global symmetry, but a completely different global symmetry, because it's global symmetry of this side tilde. Okay, and so the statement is that the fixed point, the CFT, must have a SU2 cross SU2 symmetry. And I think this SU2, this enhanced symmetry is not visible in any of the formulation, Lagrangian formulation of the theory, but it should be the symmetry of the fixed point. And this operator must belong to the same multiplet, SU2 cross SU2 multiplet of the at the fixed point, and so they must have the same dimension. That's my understanding. I might be wrong.
Okay, thanks.
Yeah. That, I think that would be a most natural answer to your question. Why in the CFT these two operators that looks very different, the same dimension, they form the same multiplet. This and the other operator as well. So I have not just this, but the whole tau A psi with A equal tau 1, tau 2, tau 3. What I have written here is just a tau 3 component of the SU2 multiplet, but the multiplet would involve also all these operators, plus a flux, a B field strength. So that is a very strong statement that in principle one can try to check on the lattice.
Yes, I had a quick question too. Going back to the heat kernel, can you see that SU2 global symmetry in the heat kernel that we constructed a few pages ago?
I'm not sure what you mean by a heat kernel.
The difference from the Lagrangian, I guess that would be my first question, is can you interpret that as the Legendre transform of some other function? And then just on this function you wrote, yeah, right there, it seems like there's an SU2 symmetry that you can see just by the signs, that there's a 2 minus signs and 1 2 plus signs. So it looks like we've projected onto the
So you're talking about this. You're talking about this equation.
Yeah, and I'm just regarding the last 4 terms as a heat kernel of sorts, because we have a Lagrangian here that we'd be integrating over some type of partition function. And so if you interpreted this right side maybe as a Legendre transform of something, then you could express it as an exact differential perhaps, that then you'd just be adding on.
I don't think it's just Legendre transform, because I have this A, right? But I have to integrate over all this dynamical field, little a, little b, and I just don't see it would be a simple Legendre transform at all. I integrate over little a, little b. The integral doesn't necessarily be determined by the 7 point, and so it's just some path integral. It's a path integral that isn't reduced to the problem of finding the Legendre transform of the logarithm of partition function. I don't think it's as simple as that. It's a non-trivial fluctuating field. It's both A and B. These are, yeah, maybe I just don't understand the language that you are using.
Should we let you finish and then revisit this in the question session? Because
yeah, I think I'm done. Yeah. Yeah.
Okay.
Thank you.
Okay. Thank you.
Yeah.
And we can continue with the questions in that case.
Yeah.
So
I guess my question is if you could if you used like a lattice derivative, if you could express this right-hand sum as an exact differential. That's what I'm asking. Or it would be exact in a certain sense. I think it's actually an inexact difference, perhaps. But
All this. Yeah. Yeah, I don't see. I haven't thought about this. How to realize this on the lattice. I'm sure these people, which I cited here, have thought about that, but their realization of the Chern-Simons terms is more complicated. It's a gauge field coupled to a lattice fermions. And so I guess I'm not able to answer your question because I don't have in my head the form of this lattice action. I'm sorry. Yeah.
all right.
And it was a very
other
inexact question, so sorry.
Maybe there is an exact thing. Maybe it corresponds to something that they do here. Basically, they have certain way to integrate out the this gauge field and then recombine the result in such a way that it becomes just a theory of free fermions.
Yeah, and that's why I'm talking about a kernel, because I'm seeing an integration having already happened over the lattice at this point. That's why you see 4 distinct states, but it's probably a wick rotated and back rotated integration curve is, I guess, how you do it. I don't know, but I'm sorry. Other people can ask questions. I'm just babbling. Thank you.
Okay. Does anyone else have a question? Okay, I guess no recorded questions. Okay, so we can stop the